This is the best use of Feynman's technique. We have this integral from 0 to infinity e to the power minus t minus e to the power minus tx over t dt. Basically, before I enter into the integral, let me introduce you to Feynman's technique. So, regarding Feynman's technique, let's say if we have an integral I from 0 to something, let's say from a to b, where a and b are constants or numbers, and if we have a function of x and t over here, let's say, and this integral is in the world of x, then we can just differentiate the integral. If you want to differentiate the integral with respect to t, then since this integral is in the world of x, we can directly differentiate inside the integral sign. So we can directly differentiate inside the integral sign, that makes it df over dt times dx. So this is what we can do, and while differentiating with respect to x, we will just make a partial differentiation assuming x as constant. So this is fx comma t, and now while differentiating, x will be constant and we will differentiate in t world and then again integrate in x world. This is what Feynman's technique is. Now let's proceed to solving the problem. We have I integral equals to integral from 0 to infinity e to the power minus tx minus e to the power it's just minus t, okay, my mistake, minus e to the power minus tx over t dt. So this is the problem. Is it t dt? Okay. So now let's proceed to solving the problem. We first differentiate it in the x world. If we differentiate it in the x world, we get di by dx equals to integral from 0 to infinity but dx of, this is partial derivative of, e to the power minus t minus e to the power minus tx over t and then dt. Okay. Now this will be di over dx is equals to integral from 0 to infinity. Now while differentiating in x world, t is just a constant, so you can take that out, 1 by t, you can take it out, and now e to the power minus t is a constant, so its derivative will be 0, and minus over here in the x world minus t is a constant, so we'll bring that in front, and e to the power minus tx will remain same. Okay, so this is the derivative in the x world. Now you can see that we are going to have some nice cancellations. D by dx is equals to integral from 0 to infinity t e to the power minus tx over t dt, and these t are going to cancel out. Okay, and then now we can integrate this thing over here to get di by dx equals to, now the integration is in the t world, so our x is constant and we will get negative x in the denominator from 0 to infinity. Now di by dx is equal to Yeah, now evaluating at infinity, we will have e to the power minus infinity. We will substitute infinity in place of t, and that's 0 and minus. When we put 0 in place of t, we'll get 1 over minus x. Okay, and then now we were having di over dx equals to 1 by x, and then di equals to 1 by x dx. So that's I equals to, if we integrate both sides, we have I equals to ln x plus c. Now to find x, to find c, what you can do is, this is our I of x. Yeah, this is our I of x. Now when x equals to 1, we have e to the power minus t minus e to the power minus t. So that's 0 dt. So a 0 dt for any limits is again 0. So we can know that I of 1 is actually 0. And we are going to use this fact now. I of 1 is 0. So we have I of x equals to ln x plus c. Okay. And I of 1 equals to ln 1 plus c. And we know I of 1 is just 0. Ln 1 is also 0 plus c. So that's why c equals to 0. And now when c equals to 0, I equals to ln x. So that's why our answer is ln x over here. And this is how we solve this difficult looking integral. And this is also the best use of Feynman's technique in such an easy way. It was no way complicated. And I hope you got the idea of differentiating on the integral sign. Thanks for watching. Look forward to seeing you in the next video.